well. So thank you very much for the three speakers that we've already had, because I think that actually lays out the groundwork very nicely for the sorts of things that we're going to be speaking about. In some ways, we're talking quite directly about the work that we've been doing in South Asia thus far, but the concepts that we've been working on actually work at a much greater level, and it's also very important to say that we've very much benefited from the existing work that's already been done by the MAEASaM project, and the work that's happening from the MAHSA Project and the Central Asia Archaeological Landscapes Project as well. So we very much consider ourselves to be building on a lot of hard work that's already taken place. In terms of there's been a whole set of questions that are actually relevant for the sorts of things that we're talking about. We have worked, I've worked in Pakistan and India. The project remit at the moment is focusing on the geographical area of the Indus River Basin, which is shown in the map on the top right-hand side, but we're also doing the Indus River Basin and neighboring areas. So in some ways, we're trying to focus on a geographical unit rather than I guess, a modern political one, but we realize that it creates all sorts of levels of complexity in terms of who and how we interact with on the ground. But in a sense, in South Asia, as in many parts of the world, there's an enormous amount of potential for the destruction of archaeological heritage. And what's very obvious is that a lot of the damage that's being done today is as a result of agricultural expansion and urban expansion. And so at a fundamental level, what we're interested in is documenting archaeological heritage and hopefully documenting it before it's damaged or lost, and also coming up with methods that will enable us perhaps to identify archaeological heritage before it's damaged, and therefore provide a mechanism, if we can work collaboratively with people, to help monitor things, exactly the sorts of things that Louise is speaking about. And at a fundamental level, the types of things that we're talking about made possible by the power of GIS and the ways that different layers of information can be combined, different specific methods can be combined to give us all sorts of insights. And in doing that, as part of our work, we've built together a sort of, in many ways, a complex workflow, but it's an integrated workflow. So we're dealing with existing records of archaeological site locations, which can be combined and cleaned and confirmed in terms of locations of sites. We're going to combine that with landscape analysis using remote sensed imagery, multispectral and multi-temporal imagery. We can make use of historical maps, all of which can be combined to identify sites that have been recorded already and sites that have not been recorded, and then combine that with field survey on the ground to ground truth the locations of sites. And in a sense, what's visible on the lower left-hand side is an example of the type of integrated workflow where we combine lots of different aspects together to produce a sort of a holistic view of landscapes and sites. And we can also combine that in a sense to look at archaeological research questions, but also create opportunities for managing heritage generally. Now, the bit that I'm going to speak about is looking at heritage legacy data. Now, if we look at the Indus River Basin and the surrounding regions, we know that there's a large number of archaeological sites that have been documented. And this map just shows you the scale of the landscape that we're talking about if you compare it to a map of Great Britain. If we're thinking about Africa, we're dealing again with an entirely different scale of landscape. So we're dealing with very, very large, extensive areas. And in many ways, we need to use methods that enable us to get somewhere in terms of getting information at a high resolution of detail, but not getting lost in the scale of the area that we're working on. So we know that there's an abundance of archaeological sites that have been identified, but we also know that there are limitations to that knowledge. Now, the traditional method of identifying archaeological sites in South Asia is what's referred to as village-to-village survey, where often archaeological researchers will go visiting specific locations and speak to local people who know the nature of the landscapes around their villages and settlements, and often follow their directions to go and visit archaeological sites. So this is shows you the location of the village of Lohari Rago and a circle around the archaeological site nearby of Lohari Rago. But we also know that there are many problems with the existing archaeological data sets. So there's a big compilation of archaeological sites that relate to the Indus civilization, which was compiled by the late Professor Gregory Purcell, and these dots are shown in orange. In 2008, we did a reconnaissance. This is Professor R.N. Singh and myself and other colleagues visited a selected number of these sites, more or less to identify sites that would be suitable for excavation in an initial sense. But what we discovered was that the vast majority of the site locations were actually incorrect. There are errors in the existing site records. And this creates problems if you're trying to manage sites and also understand the locations and the landscapes. We also discovered that there's often arguments put forward about the relationship between sites and rivers and paleo rivers. And it's very clear that certainly within Punjab, both in India and Pakistan, areas of Punjab, there is not necessarily a close relationship between archaeological sites and river channels. And it was also clear to us that there was our knowledge of archaeological site distribution was heavily influenced by the intensity of the surveys that have been conducted. So of course, areas that have been surveyed intensively have large numbers of sites. Areas that have not been surveyed do not have archaeological sites, but the pattern that we see doesn't actually resemble reality. And what was very clear was that it was obvious that hundreds and hundreds of archaeological sites have been documented, but hundreds have not. And it's very important that we start to come up with ways to systematically document these sort of sites. So I'm going to switch over now to Hector. Now let's see how I go. I'm going to try and unshare it. Hector, do you want to share your screen? And
yeah. I'll give it a try. Let's see how it goes.
If this works well, it works well.
Yeah. Okay, so
there we go.
Let's see if yes. Okay, so I'm assuming you all can see my screen.
Yes.
Okay, so we will start with we will kind of follow a chronological order in the development of our previous 2 Rains project. We started with landscape reconstruction, as Cameron has already said. The location of paleo rivers was really important for us for the analysis of the distribution of sites, but also to analyze climate change. So we, after trying several of the usual techniques for paleo river detection, none of them work very well. Actually, we only detected a few paleo rivers that were quite known in the previous literature. So we had to develop our own methods. You have to take into account this is a very large area with this is more than 90,000 square kilometers, and obviously it's including very different types of landscapes. So we also we had to develop methods involving lots of cloud computing, because no single computer could do this type of analysis. We also, just like Luis, moved to Google Earth Engine. Now we are moving into other stuff, but it was a very good start indeed. So the first way we went about to detect paleo rivers and other paleo landscape features was the seasonal multitemporal multispectral analysis that was based on the idea that paleo rivers are not always visible. They are only visible during certain seasons under certain environmental conditions. So the first thing we did, we created a new type of index, a normalized difference vegetation seasonality index, that is telling you with this scale from green to brown color which areas have more seasonal variability in terms of vegetation. So then we applied different types of spectral decomposition techniques for the areas in which there was not particularly a lot of seasonal variation, and seasonal multitemporal vegetation indexes. This allow us to find, I think it was around 70,000 kilometers of paleo rivers. Here you have in the scheme, you can see the main rivers we detected. In green was the seasonal multitemporal vegetation index, and in red you see the areas where the seasonal variability was lower. The spectral decomposition techniques were very useful. So this is a scheme of how we did this. The vegetation, the seasonal vegetation index allowed us to select automatically which areas should we use the different techniques, and then we apply them and join the results all together. I mean, in this case, we were working with thousands of images from 1984 to 2013. And this is because we choose to employ Landsat 5 because it has a very long span, so we could cover very a very long period. So this allowed us to overcome problems like cultivation change, large-scale landscape modification, and get a good idea of general vegetation health over very long periods. And you have here some of the results. In the left, you have the seasonal multitemporal vegetation index, and on the right, you have the Tessel cap transformation and the PCA analysis. As you can see, there's rivers are very visible, many of them. And we were able to trace rivers from the source almost to their end. But this was not enough. We knew there were some rivers we had not been able to detect, and some of the rivers we have been able to detect were not complete. There were areas that you could not draw a continuous line for the whole river. So we moved to a complementary type of analysis. We wanted to do a topographic analysis, but this was very complex. In the previous presentation, Rachel showed you some types of analysis for digital terrain models. Okay, we tried all of those. None of them work because paleo rivers and many other landscape structures, they have very slight topographical difference. They are very shallow, but they can be very big at the same time. So we developed this multi-scale relief model to join different cuts of the landscape, several micro-relief analysis, join them all together to create this kind of relief. Okay, so you have a comparison of different techniques here below, and the G is the MSRM we developed. So as you can see, it's the only one which offers a natural representation of the landscape and allows you to detect paleo rivers and other structures continuously, independently of how big they are. Okay. And okay, this is the result of the previous analysis, and this is the result of the MSRM. Okay, in red you have the positive relief, in blue the negative relief. I'm going to make a zoom in so you can see the differences. Okay, this is a SMTVI, a seasonal multitemporal vegetation index. You can see here in dark color the paleo rivers that are visible. Those paleo rivers actually, what the actual data you are seeing here is vegetation health, seasonal changes in vegetation health for a period of 28 years, okay? And they are darker because those rivers are showing a very particular regime. They get flooded, and they create levees, okay? And levees, the closer part of the levees, they have a coarser sediment. So this coarser sediment results in a lower agricultural production over long periods of time. Okay, so what we are seeing here are actually the levees of rivers that actually grow over the landscape. Okay, and you can see here in the MSRM how these rivers that are visible here actually have positive reliefs, whereas those that have negative relief are not visible in the SM and TVI because they are probably accumulating a much thinner sediment, and the agricultural fields on top are much healthy, let's say. So they are very complementary, these two techniques, and together we were able to document almost 30,000 kilometers of paleo rivers in the area, and we have a complete paleo river network at the moment. We have still not published the final results, lack of time, but then we moved to automated site detection. this was also a very complex type of analysis because the area is huge and we are including lots of different environmental settings. I'll show you the workflow we follow. We also employ Earth Engine. We program the algorithm in JavaScript, and we use the computational resources of Google Cloud Platform. We employ Sentinel data, Sentinel-1, which is a synthetic aperture radar, and Sentinel-2, which is optical, multispectral, of course. And then we trained our algorithms using historical maps, archaeoliterature, and also high-resolution imagery. Okay, we use a random forest classifier, and and we validated our data using different methods. This is published. It has been recently published in NAS. So and it's free to access, so anybody can go and check our results, our methods, and also the code is freely available. So it actually only needs to be copied and run in Google Earth Engine. And it's not moving. Okay, perfect. So this is the approach we follow. I'm going to explain it. We use the Sentinel-2 bands, the RGB, the blue, green, red, and then the red edge near infrared, which are very good for vegetation analysis, the short wave near infrared. And then we also use the Sentinel-1, which is a synthetic aperture radar. It's active, okay, and it's very good for physical material and has some soil penetration, which in the area we were working was useful in terms of SAMs. Okay, so we actually the final version had more images, but yeah, we can say we use more than 1,000 synthetic aperture images and more than 3,000 multispectral images. Which effectively constitute big data. Okay, every Sentinel-2 image could be up to 8 gigabytes. So you can imagine the amount of data we are talking here about. And this big data went through some data cleaning to be able to be treated. And then with these composites joining synthetic aperture and multispectral data, we use them to extract our training data, train our machine learning classifier, a random forest, and to apply the classifier. Okay, this is the selection, a small area of with some results. I developed the classifier to be in probability mode. So it's reflected here using this color scale, with yellow being 100%. And 0 being, well, the very dark color. So this is quite easy to see here. And we found more than 500 archaeological sites with very different shapes. I mean, the variability in shapes did not allow us to use deep learning methods. Although deep learning can also perform convolutions in the z-axis between the layers, let's say, these were not consistent enough to use deep learning. So this kind of machine learning approach was very useful. Okay, so from the 511 sites, only 135 were previously known, and it was also very, very cool because we found 4 new very large cities. In the Indus, only 5 large towns were known before. So we have kind of almost double the number of large cities known in the Indus. Okay. As with all machine learning methods, we only were able to detect it, the type of sites we actually trained our algorithms with. So atypical sites were not detected because they were not defined in our algorithm. Okay, even though I have to say we had 100% success, we detected all the sites we wanted to, and I think we had 3 false positives, but we cannot know if those are false positive because using validation we could not visit the site. So I imagine at least 2 of those might be sites, but they are just below dune cover. So then with the results, we obviously try to isolate it using thresholding values. You know, I mean, I think we selected more than 70% probability pixels. And then we did a morphologic filter to isolate them. And well, we did several kinds of filter, and then we vectorized them. So we got actual shapes of sites. That was really cool because it allowed us to automatically classify the sites according to size. Okay, and you can see some stats on it. So you have here an image of the distribution of sites. We also use machine learning to analyze this distribution. Okay, you have it here, the image, and this is the irrigated agriculture. So we had very few sites in areas with intensive irrigated agriculture, probably because the multispectral signal was highly distorted. And then we have the distribution of sites in relation with deep dunes. What this is telling us is that probably we have many more sites below these deep dunes. Okay, so this is also very interesting for us to know. So we have a very good detection rate, but it's clear that this is not applicable as it is, this algorithm, this method, to all other environments of the Indus civilization. So we have been working quite a lot lately with improving this method, using also emissivity data from other satellites and new types of active data, and also derived products that I have been developing on purpose to tackle archaeological sites. Okay. With these improvements, we think we can get a kind of global continental scale site detection algorithm. Okay. This algorithm will have a first stage in which it will do an unsupervised classification to divide environmental variability to specific coherent environmental zones. That is, it will not be applying the same classifier to all areas, but it would be divided according to the type, to the environmental character of the area. It will do the same with the training data. Okay, it will classify the training data in coherent groups. Okay, so you will have a specific training data which is coherent and specific areas. Then it will use the results will be filtered, and for this it will also use some kind of segmentation, and then the results of the different areas will be joined. Okay, and you have here, I don't know if it will appear. It doesn't seem to be working. Okay, here now, finally, you have here an example of an area with both irrigated agriculture and dry lands. Okay, actually, this algorithm it allows us to detect thousands of sites, and those are sites. I mean, this is not like previous approaches that were able to detect anthropomorphic soils. Those are actual sites, and those are not modern towns, because our algorithm detects and extracts and takes out actual modern towns. So yeah, we are really, the only problem is that we cannot escalate it now. It cannot be, this algorithm cannot be applied with Google Earth Engine resources because it takes too much memory. But we are now trying to develop our own hardware system to go ahead with this type of analysis. Okay, we are also working on the monitoring on endangered sites. It's a very similar system to the one that Luis presented. Actually, we should talk at some point because we are doing very similar things, and I think our algorithms can be combined effectively. In our case, the algorithm detects the type of affectation. It will tell you if it's agricultural, urban, if the site is in risk of flooding, and we are now developing the looting detection. It will also tell you when it started the site affection, for how long it has been going on, and if it has been interrupted at some point, and how close the agricultural or the urban development is to the site. Okay, you can check it automatically at any moment, although at the moment we only have a 3-day update period. This algorithm will automatically update your project databases if you have them online. Okay, it's not in your own computer. It will need to be your site database would need to be online, and it will update it and give you automatic the moment you run the algorithm on an everyday or 3-day basis. It will tell you which sites needs monitoring, what is the danger, how close it is. And okay, it's designed to be scalable depending on the availability of investment. Obviously, if you can access a satellite data provider like Planet, or I don't know, there's lots of them, you will have a much closer revisit time, like an everyday, and you will have a much higher resolution that would give you very, very great results. Okay, so it's designed for local heritage management, for people in charge of their own environment, so they can run it and have a good idea of what is going on. Okay, so that was the first part with satellite data, and now I will move to describe our approaches.
We're going to pause there, Hector, I think.
Yeah,
No?
thank you, Hector.
We're pausing there, Hector.
We're pausing. Okay, perfect.
We'll have just a brief pause. I think it'd be nice to have a pause. Just we've got time for one question.
You want questions? Okay.
I'd like to invite Sami Ullah to ask your question, please, because it's an interesting one.
Thank you. Hello, can you hear me?
Yeah.
Yes, we can. Do you want to unshare, Hector?
Yes, perhaps.
I was just asking about how can we differentiate between the historical monuments, archaeological sites, and the other settlements present in the area using multispectral images. How can we differentiate? Do we have some specific type of reflectance from these objects?
Sorry, I didn't get the question.
Hector, he asked about the ability to differentiate between modern settlements and ancient settlements. So,
oh yeah, that's an interesting question. Yes, we use the synthetic aperture radar. Modern settlements, they have walls, so they have a very high reflectance on the synthetic aperture radar. So the algorithm will automatically detect when there are walls, and would give a very low probability in these cases.
And the archaeological sites that we're looking at, often they've been damaged and destroyed, or some of them are also buried by sand dunes, and the radar can differentiate the spectral signature often from the pottery that's on the surface of the mound, or the damaged site. So it actually throws up a separate signature. But I think the main thing that we need to make sure that we're looking at archaeological sites and not something else is a training data. So we definitely need some confirmation that a specific location is actually an archaeological site. And then we can use the methods to go and find those types of sites in the multispectral imagery.
Great, thank you. So I think we'll move on now to the next section, which is covering the starting with the historical mapping. Thank you, Hector.
Okay, let's see.
I'll do this one, Hector. I start again and then.
Okay, perfect. I'll stop sharing them. Yeah.
Okay. Are we back to showing the maps? So integrated with these. The methods that we're using with remote sensing is also one of the complicated legacies of the British Empire was the fact that there was a systematic mapping program that was undertaken in many parts of the world, and as part of the British period control over South Asia, there was the establishment of the Survey of India, which set out to conduct a systematic mapping of the whole of the subcontinent. Now, one of the things that we've recognized in our work is actually something that was initially identified actually as early as the 1950s, was that often the maps that were being created by the Survey of India as a result of the systematic mapping that started in the 19th century and set out to document landscapes. And actually these maps were originally designed to have a military purpose in the terms of working out how to control access across the landscape, where settlement was located, where passes through mountains were located, and all of this had a very specific purpose in terms of documenting landscape. It developed roughly at the same time as the Ordnance Survey in the United Kingdom, which was also carrying out mapping at various scales and various levels. And what happened at the very beginning of the 20th century was that there was a meeting between military officers and the Survey of India in 1905, and the Army requested high resolution maps and full color maps of the subcontinent. And so what resulted was the production of maps like the one that you can see on the right-hand side. This is a map that actually shows a part of what was then Northwest Frontier Province in Pakistan. It's actually very, very close to Banu City, which is an area that I worked on as a PhD student. And these maps are at various scales, but the best resolution is 1 inch to 1 mile. And what you can see on the left-hand side is a map that shows the grids that were set up and the map squares, the progression of the publication of these maps over time. And you can see that there were large areas of what are now today in modern Pakistan and India that were mapped at this high resolution. Now, what was discovered by looking at these maps in some detail was the fact that these maps record an enormous range of information, and that range of information also includes the intentional documentation of archaeological heritage, but also the accidental or incidental documentation of archaeological heritage. So you can see at the top, there are a number of features that are marked on these 1 inch to 1 mile maps. We're talking about a landscape that's actually largely very flat. And we're talking about a landscape that often has archaeological sites that are preserved as mounds that exist with some elevation above the ground, but not necessarily a great deal of elevation. And what you can see on the three images across the top are the types of symbols that are used on either on the same map or on different maps to represent specific mounds. Now, these mounds were being documented by the surveyors that were doing the surveying across the landscape. Sometimes they're being marked out as stippled lines, as you can see on the left-hand side. Sometimes they're marked using what's referred to as a form line, which is not a contour, which is the one marked as letter B in the middle at the top. And sometimes they're marked with hatches, which are these little sort of triangular shapes. Each type of iconography represents a slightly different type of mound morphology. But what's clear when we started to conduct the systematic surveys that we've carried out over the last 10 years or so is that there's quite a very good correlation between these features on maps and the locations of archaeological sites. So it's quite interesting. On the lower map, you can see the location of the great Indus civilization city site of Rakhigarhi. Now, this was documented in 1905 as some sort of a village, and it also had a number of associated mounds very close by to it. It wasn't documented as an archaeological site by the surveyors, but it is actually marked on the map. And you can see in the blue circles a sequence of archaeological sites in the close hinterland of Rakhigarhi, which have subsequently been visited, and several of these sites have now been excavated. And it's very clear that these maps were incidentally documenting vast numbers of archaeological sites. Now, sometimes these archaeological sites are extremely visible. This is an example of an archaeological site called Agroha, which is in the Hisar district in Haryana in northwestern India. And you can see on the left-hand side the high levels of preservation of this site. It's not marked as an archaeological site on the map, but it's very, very obviously something unusual in this location. And if you have a look, you can actually see the area where the number 81 is indicated is a high mound, and to the lower right of that is an area with two other numbers, and you can actually see it's a standing walled enclosure, probably a fortified area of an associated area of this settlement. So we have encapsulated on these maps a whole series of information that is not been utilized systematically as a way of understanding archaeological landscapes and the distribution of archaeological heritage. Now, there's various methods that we can use to analyze these maps that provide us with useful insights. So I'm just going to stop my sharing now, and Hector, I'll get you to take up again, and you'll discuss the methods that we've been using for georeferencing and other things. You're on mute at the moment.
Okay, here we are.
You might want to go to presentation mode, Hector.
Yes, yes, I'm trying. It takes some time to actually execute whatever I press.
There you go.
Okay, so it's very noisy, isn't it? Okay, perfect. I'm going to start with the way in which we georeference these maps. Georeferenciation is the first step to actually to be able to extract information with correct geographical location. This is very important for us because we use the extraction of these mounds for the training of algorithms and for survey purposes. So, in this case, in this image, you can see the maps we have collected up to now, but there's still lots of work to finish collecting all the maps of the study area. There are hundreds upon hundreds of them. It covers a very part of South Asia. They are absolutely great because they are previous to landscape modifications of the 20th century. So, you know, with the extension of irrigated agriculture, you need to flatten out the landscape so the water can move freely. Any mound will be the presence of a mound will disturb this water distribution. So many of them were flattened out in this map. Many of them are still standing. But there are also lots of features that could be of interest. Okay. However, it was impossible for us to extract data manually from all these maps. It would have taken lots of hours and lots of people because you have to go. I mean, the scale is very big, the 1-to-1 inch mile series, and you know it takes quite a lot of time, and it's also very difficult to cover the whole area systematically. Okay. Because you need to create a grid and go systematically one cell by one cell, and in order not to leave any feature. There are also inconsistencies in the features extracted by different people. Some people would, the bigger sites are pretty evident, but some sites, you know, you might think this line is not that clearly a mound. So depending on how many people are actually extracting the features, you get different results. So we thought the best way to go about was to actually train an algorithm to automatically extract features of archaeological interest from all these maps. But, well, sorry, I think I'm advancing. You have some examples here of different editions of the type of features we are interested. These are mounds, all of them. And yeah, here it is. So this algorithm, we develop an algorithm for the extraction of mounds. As you can see, we also limited the algorithm to 2 hectares because something smaller than 2 hectares tended not to be a site. Okay, so in this way we save lots of work. Actually, you see here the algorithm we were using is a RCNN. We have been trying mask RCNN because we are not just interested in detecting site. We want to extract the shape. so we can automatically analyze the size. Okay, actually, the algorithm we use for this analysis is UNet architecture, not Masker CNN, although now we are moving to Masker CNN. Okay, so this algorithm provided, depending on the type, we develop different detectors. This is a work led by Arnau Garcia, which is I hope he's with us today. Okay, and we also collaborated with Dharam. But well, the results of the algorithms are pretty good. We get from 88 to 96% success. That is, depending on the specific algorithm, for the size you can have from a 12 to a 4% of false positives, and from a 5 to no missed site. Okay, so the results were absolutely excellent. They are going to be, well, the paper is already accepted. It will be published hopefully soon in the Journal of Archaeological Prospection, and we in this paper also we work with French maps, and we try different types of features. For example, we have developed a detector for the word tell, and it works pretty well. We had very little training data, and it had excellent results. I think with a few more training data, we can just map all the word tell in different languages. In all the map series, we are also started to work with Russian maps. So we think this I mean, we want to go for big series of maps because the French colonial series, the British colonial series, and the Russian series cover big areas of the world, and in this way, our detectors can be employed on very different situations because they are consistent with the way in which they identify sites. Also, we are working on the development of detectors for specific features like water sources. And okay, we think this has an enormous potential. I have to say though that the thing that we have not managed to automate is the georeferentiation process, which is very complex. And because those are not the deformations on these maps do not follow a mathematical pattern, so you need at least 20 well-distributed ground control points, because if the deviations are too big, then you cannot use this data to automatically compare with the results of the remote sensing, and you cannot use this data to go to the field to actually check the sites. Let's see if it's not moving. See. It kind of hung. Okay, so yeah, that's it. Okay.
Time for a pause again.
Yeah, perfect. Okay, so if there's any question.
Yes, thank you. We have one question from Ata Rahman. So if you are able to unmute yourself and ask your question.
Can you please hear me?
Yes, yes, thank you.
Yes.
Okay, thank you. This is Ataur Rahman from University of Peshawar, Pakistan. It's very interesting presentation regarding the remote sensing application in archaeology. But as a geographer in Pakistan, there is a rapid changing climate scenario, and there is high frequency of hydrometeorological disasters, and there is serious threat to the archaeological sites. I, as a geographer, would like to put a question is, how far it will be useful if joint venture, I mean the multidisciplinary cross-cutting scientists, to work on monitoring impact of climate change and disasters on endangered archaeological sites. Like for example, Harappa is one of the archaeological site which is on serious threat to the waterlogging and salinity problem, which is a human-induced disaster. and they are a serious threat to this particular archaeological site. Similarly, Takhbai is another archaeological site exposed to monsoonal shift, and there is intense rainfall, particularly in that particular region. And due to its location, it is very much endangered situation. So I wish that there should be a joint venture of the geographers who know the hydrometeorological aspects, and they could jointly work with the archaeologists to explore the impact of these disasters and the hydrometeorological disasters on these endangered archaeological sites. It was very interesting presentation by Hector and Cameron. Thank you.
Oh, thank you. Well, I cannot but agree.
Thank you very much, Atta Rahman. I mean, I think that from our side, yeah, I think there's definitely scope for collaboration and interaction on this front. And that's very much why we want to engage with you in like starting with this conversation like today. I think exactly the thing that Louise Rain mentioned earlier and Hector about the monitoring, it is possible to detect change that's occurring at quite a rapid pace. So one of the things, Hector didn't really describe it, but we're conscious that there was actually a very strong winter rainfall season and also a summer rainfall season in the last 12 months. And looking in areas of Cholistan, there was actually a very substantial increase in the amount of land that was being brought under irrigation agriculture. So we can actually detect those sorts of changes where influence of, high levels of rainfall are affecting what administrators and farmers are doing on the ground, and therefore try and do something in terms of raising awareness about that. Because I think the Pakistan and India are such vast countries, it's very difficult to maintain monitoring of everything. But I think using these digital methods, we can actually recognize change. So I think the work that we're describing at the moment, we're very much focusing on an archaeological component, but to understand the archaeology properly, we need to understand the rainfall, the landscape, the hydrology, and all of these things. So it has to be multidisciplinary in terms of getting a good understanding of everything. So I think it's a very good question, and thank you.
Great, thank you. We have one question, another question from Kevin McDonald. If you could ask your question, please.
Hi, hello. I mean, it's great data, and I'm very impressed in the previous lecture about, you know, what can be done in terms of with the TandemX data in terms of beginning to, you know, work out some of these settlement mounds. But I do wonder about some of these detection algorithms, if in a sense they're really time economical, in that, you know, you have missed sites, you have false positives, you know, humans have to check them, and you have a lot of laborious coding to arrive at something that works. In terms of time, if you just started out, I mean, having, you know, in fact, 3 or better decades of working with aerial photographs and satellite imagery and doing surveys in West Africa, I can work pretty fast, and someone who's well trained can work pretty fast in finding these sites in terms of doing the remote sensing. Do the algorithms really save you that much time in the end?
Yes.
A one-word answer. I think
it will be, I mean, we are working in terms of, look, I will answer both questions with because you made a previous question, I believe, about the presence of modern towns on top of ancient settlements. If we eliminate these modern towns, we lose the modern settlements. But exactly. we have very high resolution. So I'll try to share the screen and see if I can show you. Yeah.
I guess the other answer to your question, Kevin, is that
at some point someone has to go to the field and see what the features actually are. Someone has to see what's actually there. So our workflows had a major ground truthing component to it right from the beginning. And the idea was to set up a methodology that allowed you to get to sites quickly, see what was on the ground, record things quickly, and digitize everything and have things assessed in a very rapid fashion, but also provide some sort of indication of what the feature actually was, or what the cultural component or chronological component of the material culture you're looking at was actually about. So this is one of the archaeological sites from the surveys that we've done. You can see it's a mound surrounded by agricultural fields. This is actually kind of a rare form for archaeological sites to take in most of Haryana. All right, so this is what I'm talking about. We come in through all these various sources of data that we have. We basically have assembled a database of thousands of potential site locations. Every single one of those white dots is a potential site location. And there's just no way to visit all of those locations. There's no way to record all of those locations off the bat for a single team. So obviously a sampling strategy was needed. So you can see the blue shapes are actually the locations of previous archaeological surveys in Haryana. So you can see the white dots represent mostly historical map features that were pulled from some of the work that Hector described. So you can see that just in this area, which was ostensibly covered by previous surveys in Haryana, there's nearly 10,000 potential site locations. So what we did is we actually devised a strategy for sampling all of the different locations within very specific areas in this region. So if you see those white hexes, that they're falling in between surveyed areas, they're falling in areas that have surveyed. The idea was to treat specific arbitrary geographical grids in exactly the same way. So to have a systematic approach to ground truthing all these various sources of data. So it worked fairly simply. We took the database of previously recorded sites. You can see these 4 boxes here. The database of previously recorded sites. We combined it with remote sensing features. So some of them were extracted in early versions of some of the automated detection algorithms Hector was describing. We also took village to village discoveries. So within each of these hexagonal regional grid units that we visited, we made sure to touch base with several of the villages in the area and systematically record any locations known to people in those areas. And then finally, historical mapping features. All this was fed directly into sort of a GPS capable system where we could actually sort of drive out in the landscape and start ground truthing various features. So the idea was once we arrived, so we put all the data together, export it into a CSV file that goes into a tablet. And on the tablet, we visit each location and assess it. And then we systematically do surface collections on the surface of each site that then feed back to that first location form. All this is done in Open Data Kit, ODK, and is held on a tablet that's then uploaded into the laptop in the field. And that once we collect data from surface collections, systematic surface collections on each site, we actually do rough assessments of the material culture. So we review materials that we collect in a systematic way across each potential site location. And these are separate forms that we use. So we use a master location form, surface collection forms, and assessment forms. And it all feeds back into a database and then goes into the laptop, and you kind of get this cycle that you can use to do the ground truthing. So obviously this is kind of like the ideal sort of site morphology in Haryana. This is just an unoccupied ancient settlement with some agricultural fields to the side. Usually the agricultural fields actually cut in. You can actually see they're starting to cut in here. And most of the time in the field, you actually have this sort of terraced mound feature, which isn't quite so obvious when you visit it on the ground. All right, so upon visiting each site, we mark a central location. So this is the area where you determine whether or not a site is actually present. So in this instance, a site is defined by a number of confirmable antiquities within proximity of each other. And then once you've defined a site, so once you've made a location form, you walk on 2 transects. We just did simple north, south, east, west transects. Walk either until you encounter something that prevents you from walking, or you get a series of negative surface collections. So at either 50-meter or 100-meter intervals, you can see here, all the material in a 1-meter radius was collected from the surface of the site. And we basically do this, that you get sketch maps in the tablet that we prepared, but then all of this is actually fed into a material culture database, real time in the field. So that obviously gives you a much more systematic view of what is on the ground. So this is the site you saw before. You can see there are areas where there's good visibility. There's a lot of material on the surface. So you get large amounts of material culture uncovered. So this is kind of like an obvious site. You can see the steep drop off once you get into the agricultural fields at the side. And then you also have here, you can see this is actually a site location that isn't present in using any of the remote sensing sources that we've experimented with so far. This is what we would call a terraced mound. So this was a mound like this at one point, but it's all actually been cut down. Luckily, there's still material culture evident on the sides of each of these agricultural fields. So using this sort of ground truthing method, that material is still collected, and we still get kind of a database footprint that we can subject to sort of further analysis. So this is a view of the structure of Open Data Kit. So Open Data Kit is basically just a digital form platform designed to record information on the field in a tablet and hold it in case there's no internet connection, so you can upload it into sort of a cloud server. We use a Google Cloud server. And each form has sort of a series of fields. We use the location form, location ID. This feeds back to the surface of data, or to the source of data that it was collected from. So you can see here's our 4 sources of data that we use to identify potential site locations. We visit the locations, record their coordinates, take a photo, record information about any informants, and then you can see all the way here you get to the determination of whether or not there's actually an archaeological site present. So this means that for all these locations that were recorded either on historical maps or through the automated site detection, where there were no sites, we've actually recorded that data, which becomes another source of information we can use to sort of go back and improve the automated detection process. Then you can see we drill down into a series of more specific questions about the site. Then obviously we do these surface collections. So rather than arbitrarily collecting materials on the surface of the site, surface collections are taken systematically along usual transects. So you have the location form at a central location. Then when you do the north, south, east, west transects, and all of these are just marked very simply in the form. And then once we collect those in the field, all that's bagged and taken back, obviously. So we get to our field camp. This is something some of the field crew, so all the people we've worked with are here in this workshop today. All this material is then counted and then analyzed very in a preliminary fashion and entered into a field database, which we can sort of use to do further assessments. So as a result, you can see in the Two-Rains survey area, which is what's depicted here in these hexagonal grids, 264 of the approximately 1,000 locations that were visited actually turned out to be archaeological sites. And we have sort of a rough assessment of some of the features of those sites, whether or not they're intact mounds, terrace mounds, completely flat, irrigated, destroyed. There's all kinds of different categories we use to classify all the various sites we encountered. Okay, so I think at that point, I switch it back over to you, Cameron.
Thanks, Adam. If you need to, hang on. Just do that and I will switch over and just finish up. So I guess the important thing to try and say at the end, is that sharing correctly? So the important things to say at the end is that this, hopefully the workflow that we're describing has a lot of potential in terms of being able to document archaeological heritage sites, but also conduct research and conduct research at one level, but also manage that heritage resource at another level. Now, it's useful to sort of highlight from my perspective that the whole project that we're describing came out of a research project that has been running since 2008. And with the research project had a specific aim of trying to understand the relationship between humans and their environment, and also trying to understand how the relationship between humans and their environment has changed over time. So these are collaborative work between Banaras Hindu University and the University of Cambridge researchers. And as Adam mentioned, there's a range of people that are watching at the moment that have been involved in this work. Now, I'm not going to talk about all the survey results that we've done in detail. I just want to make some quick observations. We've conducted a combination of landscape work, settlement survey distribution, and also excavation. So it's an integrated method, and we're also working with geographers and earth scientists as well. So it does sort of fit with what H.Orengo was saying before about the opportunities of working cross-disciplinarily. But in a sense, what's interesting for us is that by looking at combining things like Hector talked about, hydrology, landscape reconstruction, we can actually understand the nature of hydrology in river systems, the way those river systems have moved and potentially damaged the locations of archaeological sites, and also the association between sites and hydrological features. Now, I'm just going to quickly show you, these are some time slice images. This is the pre-urban Indus period. You can see there's a distribution of archaeological settlements. Some of them seem to be associated with paleo channels, some of them do not. When we see the appearance of urban settlements, we seem to have the abandonment of settlements in certain locations and the consolidation of sites into particular areas. And there seems to be sites located quite close to the city of Rakhigarhi. After the decline of Indus urbanism, we see a further redistribution of settlement across the landscape, occupation in new areas, different settlement, signature landscapes developing in that period in time. And then we have a change in the nature of organization. We move into other chronological periods. Painted Greyware period, we see again a change in the settlement distribution. But what's very interesting is that a lot of the research that's been carried out in the Indus River Basin particularly has focused on the Indus civilization and its associated settlement systems. What's often overlooked or possibly missed is the fact that the majority of archaeological remains in the region actually date to the historic periods. This is the distribution of early historic settlements, which we know about. So these are settlements that date from around 2,500 years ago up to around 1,500 years ago. And then we also know that beyond the early historic settlements, we also have an abundance of medieval sites. So sites that date from around 500 AD up until the more recent periods. And then on top of that, we have modern villages as well, many of which are sitting on top of these medieval or early historic sites. And it is apparent, it's evident in many ways that many of the earliest sites are not being occupied by later occupation, at least as far as we can tell from the surface material. So hopefully what we have is, what we're trying to develop is a transformative way of combining archaeological research with heritage documentation and management. And we wanted to outline to you this integrated workflow that combines a whole number of different sorts of streams. We're really hoping to collaborate with government archaeological authorities, academic institutions, and also especially PhD students, and create opportunities to offer training through workshops, training in GIS methods, training in the remote sensing analysis and site detection approaches that we've described, training in the methods that we're outlining in terms of the historical map use, and also training in the field methods. And we're very keen to, in a way, to collaborate and engage with people with fieldwork, and to empower people to carry out their own fieldwork and ultimately contribute to a centralized repository that can be used by heritage managers and also archaeological researchers in a way of trying to get a much more holistic understanding of the distribution of these archaeological sites and what it ultimately means, but also to try and protect as much of it as we can in the face of sort of increasing agriculture and urban expansion, etc.